We've been taught to think of the internet as a weightless cloud, an invisible layer of data floating somewhere above us, accessible by magic. In reality, of such scale that its data centers consume more electricity than many mid-sized countries. Every financial transaction, every emergency broadcast, and every social interaction we have depends entirely on this subterranean and submarine hardware. We spend our lives interacting with the interface, while remaining almost entirely unaware of the massive mechanical effort happening beneath our feet. Consider the exact moment you finish typing a website address and your finger strikes the Enter key. In the few hundred milliseconds before that page appears, your request must navigate a global gauntlet of digital and physical obstacles. That single strike of the key sends a pulse across your room, through your walls, and begins a high-speed transit across the planet. Before the journey begins, your computer has to solve a translation problem. While we use names like youtube.com, computers only recognize specific numerical coordinates known as IP addresses. This is where the domain name system, or DNS, steps in. It functions as a master directory, instantly converting the words you typed into these numbers, so the network knows exactly where to send your signal. Once your device has these coordinates, it pinpoints the specific server on the global grid. Without this background directory, navigating the web would require you to memorize a unique 12-digit string for every single site you ever visited. Once the destination is set, your device breaks your request down. It chops the data into millions of tiny, uniform pieces called packets. When you send an email or load text, the system uses a protocol called TCP. It prioritizes accuracy. If a single packet goes missing on the track, the system waits for a replacement. But for a video call, the protocol shifts to UDP. If a packet is lost, the system leaves it behind to maintain real-time connection. The internet is constantly toggling between these two methods, choosing whether to favor perfect accuracy or raw speed based on what you're doing. Those packets leave your device as a wireless signal, but that wireless journey is short-lived. Within milliseconds, they reach your router and enter a world of copper and glass. The signal is now a pulse of light, traveling through fiber optic cables buried under city streets. These glass threads move data at near light speed. Your request passes through massive industrial data centers, warehouses filled with thousands of humming servers that act as the traffic controllers for the global web. To reach a server on another continent, your data must dive. It travels through heavy, armored cables resting in the silent, freezing dark of the ocean floor, thousands of feet below the surface. Every wireless interaction we have is actually tethered to this vast network of submerged metal and buried glass. Because this journey relies on public cables and shared hubs, the data is physically exposed. Any node along the path could theoretically listen in on the packets as they pass through. This is why your browser uses HTTPS. The moment your data enters the network, it is mathematically scrambled into a randomized mess of shapes. It only becomes readable again at its destination, where mathematical instructions snap the pieces back into order. This invisible layer of math is what allows us to send bank details, passwords, and private messages across a public, physical infrastructure without being intercepted. Your request finally arrives at the target server. In an instant, that server retrieves the data you asked for and fires it back along that same thousands of miles long path. Your device catches these returning packets, reassembles the scrambled code, and begins drawing the images and text on your screen. The entire process, the translation, the intercontinental journey under the sea, and the mathematical scrambling, is completed in less time than it takes to blink. But the scale of this machine is reaching its limits. As billions of new devices and AI systems come online, the physical demand on these cables and data centers is growing exponentially. Keeping up requires constant physical expansion. We are now building data centers with massive liquid cooling systems and experimenting with quantum processors just to prevent the physical glass and copper from overheating under the load. The internet isn't a magical abstraction. It is an ongoing human project, a fragile physical architecture that requires thousands of people and massive amounts of energy to maintain every single day.